Kim Jake Tiani. Welcome to Cooler Facts, the show that's full of surprising facts about the world around us. The first surprise is how we're telling you our stories. Fasten your seatbelts for a fun ride of fast-paced video bits. Each one will leave you with something new. We're gonna tell you everything you didn't know about living in space, why rain should be the least of your worries of things falling from the sky, and what natural disaster you'd never find at the equator. First up though, and I do literally mean up, some cool facts about skyscrapers, such as how long does it take window washers to clean all that glass in one of the tallest buildings in the world?
Nothing conveys the remarkable heights of human ambition quite like the skyscraper. That ambition has translated into an endless global battle to build bigger and better ones. But just how high can we climb? The intense competition to produce the world's tallest skyscraper began with the invention of the safety elevator in 1856. There were elevators before, but they were simple platforms hoisted up by cables. If the cable snapped, they'd plunge to the depths. Inventor Elisha Otis came up with the idea of attaching special vices that would clamp into place when a cable broke, holding the elevator up. The Bessemer process represented another major advance. Steel, an alloy of carbon and iron, had been around for centuries, but it was always too expensive to produce. In 1855, Henry Bessemer came up with a less costly way to do it, by blowing air through molten iron to remove the impurities, giving steel its signature look. Another giant leap came in 1871, the year of the Great Chicago Fire. Devastating at the time, but not in the long run. The disaster destroyed 18,000 buildings. It also turned Chicago into a hub of building technology. Overnight, Chicago transformed into a gleaming, towered metropolis. Ground value grew from a few $1,000s to more than $5 billion. Today, it is home to some of the greatest buildings of the 20th century. By 1930, the world's tallest building was this, the Chrysler Building in New York, a tribute to the auto. The stainless steel exterior resembles a car's chrome. Here, on the corners of the 61st floor, are replicas of the 1929 Chrysler hood ornament. And down on the 31st floor, replicas of the 1929 Chrysler radiator cap. In 1931, New York's Empire State Building stole the tallest title. 381 meters high, it reigned supreme for 41 years. Then, in 1972, the World Trade Center opened, height to its roof 417 meters. 2 years later, Chicago's Sears Tower shot up by about 25 meters. On a clear day, from its sky deck, you can see 4 states: Michigan, Indiana, Illinois, and Wisconsin. In 1998, Malaysia's Petronas shot up 8 meters over the Sears Tower and stole the world title. It takes 2 window washers 2 months to clean all its glass. The Taipei 101 in Taiwan now towers over all the rest. It's 509 meters tall. No ordinary box of glass and steel. It can withstand a Richter 7 earthquake. That's important. It sits roughly 2 blocks from a major fault line. Even Taiwan's famous typhoons and fierce winds are no match for it. Thanks to this, a tuned mass damper, the world's largest and heaviest, weighing in at 730 metric tons. Seismic vibration causes its enormous sphere to shift, at which point its 8 viscous dampers act like shock absorbers. The device then counteracts the building's movement by making it sway in the opposite direction of the force. But another building is rising in the desert that will surpass it. The Burj Dubai in the United Arab Emirates, slated for completion in 2009. Its exact height is top secret, but experts say it will soar up at least 700 meters. If it does, it'll be the tallest man-made structure of any kind in history. The Burj is the crown jewel in Dubai's massive building boom. Industry experts say that about 30,000 construction cranes are in operation here. That's 24% of the world's 125,000. If you think the Burj marks the end of the sky race, think again. Right now, plans are in place worldwide to fulfill the dream of the mile-high building. That's 1.6 kilometers, or 1/10 of the way to the ozone layer. Right now, it's just in the dream phase, but the technology is in place. Skyscraper builders are just waiting for the nod. So are the window cleaners. There will be lots of windows.
Wow, I can't believe that 25% of the world's cranes are in Dubai. The sky really is the limit, and as you're about to see, there is no limit to what can fall from the sky.
Many people think Henny Penny screaming, "The sky is falling," is nothing but the hysterical rambling of a chicken. However, Henny Penny may have been onto something. Consider what happened in August 2004 in Shropshire, England. Just another stormy day until the clouds opened up and down poured fish? Yes, about a dozen live minnows were picked up by a combination of strong winds and a waterspout over the ocean, and then dumped 80 kilometers inland, on an unsuspecting parking lot to be exact. In fact, fish, frogs, and other small creatures are often swept up in this manner, but you might prefer those critters to an encounter with blue ice. You know that blue liquid disinfectant in toilet bowls? Well, blue ice is the sanitized term for the chunks of ice that form from leaks underneath airplane holding tanks. And yes, it does include human waste. Most often it melts and dissipates over wide swaths of ground. But if that's not disgusting enough, on occasion big chunks of blue ice and feces smash into the ground, damage houses, and dent cars. Speaking of man-made aerial hazards, when it comes to scale, nothing outdoes Skylab, America's first space station. It fell to Earth over Australia in 1979, but since most of the debris burned up on re-entry, no one was hurt. Australia did, however, have to deal with space junk cleanup and ended up fining the US $400 for littering, a fine which is outstanding to this day. A newly identified, yet largely mysterious phenomenon called meteors may be the most dangerous thing falling from our skies today. They are large hailstones that form in the atmosphere and weigh up to 4 kilograms. That's 4 times the size of the largest recorded hailstone, and about the size of a healthy newborn baby. The mystery lies in the fact that meteors fall from clear blue skies without any warning. Italy and Spain were impacted by a rash of them in January 2000. Although no one has yet been killed by the meteors, a Spanish woman from Almeria was struck in the shoulder and knocked unconscious by one. And no, her name was not Henny Penny.
I can see future weather reports now. Feces with the afternoon chance of Skylab. Coming up next on Cooler Facts, a natural disaster with the force of 200 cars traveling at the speed of a 747. Don't blink. Welcome back to Cooler Facts. We've all heard the saying, war is the mother of invention. And nothing could be more true than with the development of the bomb. Here are some startling facts of how the bomb has developed over time and how even bats and rats have played a role.
Throughout history, humans have found very creative and curious ways to blow things up. Some of the first bombs date back to the Crusades. In 1095, armies defended their castles using clay pots filled with flammable liquid. Soldiers lit them on fire and hurled them at their attackers. The first hand grenades. Weapons development really intensified when armies took to the sky, dropping explosives on their enemies from the air. The first aerial bombs rained down from balloons. Zeppelins or airships were used to bombard England during World War I. Down on the ground, the British were disguising bombs in rat carcasses. Special agents would hide the rodents in wood piles next to boilers in German factories. In went the wood, and the factory would go up in smoke. During World War II, the US hatched a plan to bomb Japan using bats carrying time bombs. Bats, after all, can carry up to 12 times their own body weight. The idea was to drop them over mainland Japan at night. They would then find a place to curl up and sleep in or around buildings during the day. Then the bombs would explode. That was the theory, but the bats proved to be unreliable, so the whole project was dropped in mid-1944. Welcome to the nuclear age. By the 1960s, the Soviet Union came up with this behemoth, the Tsar, 8 meters long by 2 meters in diameter. It had a yield of 50 megatons. That's equal to all the explosives used in World War II, times 10. It was detonated in 1961 over an island in the Arctic Sea with frightening results. But nothing is more frightening than the idea of the cobalt bomb, a hydrogen explosive coated with cobalt, the fallout from which would kill all life on Earth. No superpower admits to ever having one or creating one. After all, what's the point of killing everything? Still, the doomsday bomb is well within our technological reach. When it comes to bombs, it would be our greatest achievement, but no one would be around to celebrate.
Although not quite on par with blowing up the whole world, nature also can pack quite a punch. When it comes to natural disasters, hurricanes and earthquakes immediately come to mind, but nature's most powerful fury comes in a different package.
Avalanches are so violent that when they strike, researchers treat them like crime scenes. About 1 million avalanches occur each year. In 2005, a 500-meter wide shelf of snow and ice tumbled down an Alaskan mountain. Its volume was 400,000 metric tons, enough debris to fill about 22 football stadiums. It would take 75,000 dump truck loads to move it all. Avalanches can splinter trees into toothpicks, blast roofs off houses, and hurl trees through walls. In one case, the force of an avalanche wrapped a cargo van around a tree, its front and back end kissing each other. It had been flattened into the thickness of a phone book. Turns out the avalanche is not only one of nature's most fearsome weapons, it's also its most powerful bulldozer. In 1999, an avalanche buried the Austrian resort of Galtur. Its mass weighed upwards of 300,000 metric tons and roared down the mountainside at nearly 300 kilometers an hour. A healthy snowfall over your average-sized house weighs as much as a car. Now imagine over 200 cars coming at you at the speed of a 747 taking off. All avalanches are due to a weak layer below giving way to a heavier one above. Between these two layers, experts at Galtur discovered something called a saltation layer, a tumbling mixture of light and heavy snow. This newly discovered layer causes the avalanche to increase in volume as it descends. It works by churning the layers of untouched snow beneath and binding with them, creating larger and larger particles, increasing the gravity of the falling snow mass, and therefore the speed. Here's something to chew on. If you happen to get caught in an avalanche, there's a 95% chance that you were the trigger.
Maybe that's why I don't ski. Cooler Facts will be right back. Stay right there. Welcome back to Cooler Facts, the show that unearths the hidden treasures of science and technology. I'm Kim Jagtiani. It seems inevitable that humans will one day be living in space. Sounds good to me. The view's gonna be spectacular. I've always wanted to float around in zero-G. And if you like more than one sunrise a day, this is the place for you.
So you want to travel to space. The view alone is worth the trip, but be careful what you wish for. Living up there presents many challenges, and that's an understatement. The right suit is essential, especially for a spacewalk. NASA's EVA, or Extravehicular Activity Suit, is up for the job. Essential, but not cheap. It costs $12 million. Well worth it. Without its pressurized comfort, you wouldn't last long. In the harsh vacuum of space, lack of oxygen in the blood causes death within 2 minutes. The hardest thing about living in space is that you must rely on people on the ground for everything, which is one major reason NASA hasn't yet returned to the moon, even though they are itching to. The expense of carrying essentials is a major hurdle. Shuttling just a kilogram of water to space costs about $5,000. So instead of flying it in, the space agency is developing a machine that will recycle astronauts' urine and even exhaled breath and turn it into drinking water. The device will purify these fluids using chemical membrane osmosis. By this process alone, all 7 astronauts on any given mission will have all their daily water needs covered. They'll need all that water to wash down the spicy food. One of the mysterious impacts of zero gravity on the body is that it blunts the palate. Food tastes flat and bland, so astronauts pile on the seasonings. Members of the Space Shuttle STS-46 mission in 1992 revealed that small packs of hot sauce became a medium for barter. If you were up for latrine duty, hot sauce could get you out of it. Salt and pepper is available, but only in liquid form. Ordinary salt and pepper particles would float up and clog vents. Living in space has its advantages. One is that it makes you taller. Decreased pressure on the spine causes astronauts to sprout about 5 centimeters. It can also cure snoring. A 2001 study says snoring stops once you're up there. Down on Earth, snoring happens when the tongue drops to the back of the throat, partially blocking the airway, causing tissue to flap. Of course, gravity does not exist on any spaceship, yet. No gravity, no tongue blockage, and no snoring. But still, you won't get an ideal sleep up there. The sun rises 16 times a day, throwing off your inner time clock. Despite recycling your own urine, the bland food, and poor sleep, traveling to space remains humankind's most enduring dream and the most prized experience to anyone who has made the journey. Just look at America's first spacewalker, Ed White. He described being ordered back inside his Gemini craft after a daring extravehicular walk as the saddest moment of his life.
Okay, the view is unbelievable, but living in space isn't going to be easy. Then again, living here on Earth isn't that easy either. We picked some pretty crazy places to live on this planet. For instance, how do you protect a city that's built on a floodplain?
All the people on Earth, 50% of us live in cities, but they're not always in the most ideal location. So some builders have developed extreme ways to cope. The Dutch city of Rotterdam is under the constant threat of flooding. The solution is a gigantic sea barrier with arms that are 300 meters long. They're each as long as the Eiffel Tower is high. But each arm is 4 times heavier than the tower. In a storm, the huge gates slide into place in under 2 hours, blocking the rising water that could threaten the international harbor. In New York City, they're also worried about water, but it's drinking water. The 2 old tunnels that deliver the city's water are leaking and can't keep up with the demand. That's why for 50 years, workers have been digging a huge 90-kilometer-long third tunnel. It stretches from a water reservoir north of the Bronx to right under Manhattan. The tunnel will be at least 150 meters underground, 10 times as deep as the subways. When it's complete in 2020, it will supply New Yorkers with 19.2 billion glassfuls of drinking water a day. In nearby Hong Kong, they were faced with landing a jet plane on one of the most crowded islands in the world. Before 1998, landing at the former Kai Tak Airport was notorious. At just 100 meters above ground, heavy jets needed to make a quick 40-degree turn to hit the runway that lay in between the dense jungle of apartment buildings. Planes came so close to dwellings that passengers could actually see people doing their laundry. The solution was not only to build a new airport 16 kilometers from the city center, but to build it out of rubble. Demolition crews flattened 2 hilly islands and filled the gap between them with the excess material to create a mostly man-made surface. In Montreal, where winter temperatures dip below minus 20 degrees Celsius for weeks on end, the solution is 32 kilometers worth of underground city. It's the world's largest underground mall, and it covers the same area as 11 championship golf courses.
Looks like it's all about location, which is also true about hurricanes and cyclones. Now, which one is which? We're gonna find out right after the break. had a pretty powerful show so far. Avalanches, bombs, things falling from the sky. Let's say we finish up with something a little bit more mellow, like a hurricane.
Packing more punch than a nuclear arsenal, hurricanes are one of the most powerful forces on Earth. All the TNT ever produced doesn't hold a candle to the muscle of Mother Nature. Measuring up to 900 kilometers across, a hurricane's powerful winds spiral inward and upward from 118 to 320 kilometers an hour. Those top winds flatten concrete buildings in seconds. Fueled by the evaporation of seawater, a hurricane releases huge amounts of energy as vapor rises and then condenses. An average hurricane releases the heat energy equivalent of 200 times the total annual global production of electricity. In the northern hemisphere, a hurricane's winds rotate counterclockwise and drift to the right. It's a result of the Earth's rotation creating the Coriolis effect, a force that causes cyclones to spin and turn towards the North Pole. The opposite happens in the southern hemisphere. Cyclones spin clockwise and drift left. But there's no middle ground. There's almost no Coriolis effect near the equator. No spin means no hurricanes. The destructive intensity of a hurricane doesn't depend on its size. It's if and where the hurricane hits land. Hurricane Camille was the strongest tropical cyclone on record at landfall. In 1969, a Category 5 hurricane, the highest, hit the Mississippi coast with winds over 305 kilometers per hour.
All right, time to blow on out of here, but not quite that fast. We'll see you next time with the facts that will floor you, from the world's scariest roller coasters to animals with heads the size of cars. We'll see you next time for Cooler Facts. I'm Kim J. Tierney.
Welcome to Experimental, the science show where women torture men with big pricks. Men lift other men's kilts in search of intellectual satisfaction, and goats get all stiff and fall over. Coming up, conclusive proof from the test department that toast really does land batter side down. And we move the location of the penis back to its rightful place. But first to Dublin, Ireland, where Experimental is asking a pointed question. What don't you like about going to the doctors?
Needles. The needles. Needles.
Needles. Cold hands.
Hang on, what was that?
Needles.
All right, that's better. Yeah, no one likes being jabbed, especially when it's what the medics call an intramuscular injection, i.e. in the bum. But hey, at least you're getting your medicine, aren't you? Well, not always. According to the research of a woman who's pricked more bums than most, Dr. Victoria Chan of the Adelaide and Meath Hospital in Dublin.
I have personal experience of patients having pain medication or anti-nausea medication injected, and an hour later the nurse would come back to me and say that it didn't work. The patient is still feeling pain, the patient is still feeling sick.
It used to be that bums were a really good place to inject drugs. The problem is that bums are changing. In the West, at least, backsides are getting fatter, which means that needles will have to penetrate further to deliver the drug to the underlying muscle.
Now, this is a 3 centimeter length needle, or 1 1/4 inches, which is the approximate length of the most commonly used needle for intramuscular injections around the world. Now, what the needle is going to do is go through the skin, through the layer of fat, and into the muscle. Depending on how much fat is overlying the muscle will dictate whether this needle is long enough to reach the muscle.
So maybe, and you are not going to enjoy this, the needle is not long enough. To find out, Dr. Chan enlisted 50 patients, each willing to allow her to add a little extra something to their normal bum jab.
Each patient received the medication that was prescribed by their physician along with a small amount of air so that we can see a black air bubble on the CT scan.
But isn't that deadly?
No, not at all. First of all, it's a small amount of air, and also when we are injecting, we pull back on the syringe so that we know we're not in a blood vessel, because it's only if we inject air into a blood vessel that might be a little bit dangerous.
Only very slightly inflated by Dr. Chan's needles, the patients were inserted into a CT scanner, which revealed where the bubble solution ended up.
So what you see on this screen here is the CT scan. You can see here that this is the skin, this is the layer of fat, and this is one of the gluteal muscles of the bum. This black thing here is the air bubble that we had included with each injection to the patient. This air bubble has remained in the fat, so this would be considered a failed intramuscular injection because the medication has not reached the muscle where it's supposed to.
In fact, of her 50 bottoms, she found out that the right amount of bubble solution reached the muscle in only 56% of male behinds and only 8% of female butts, which is a bit of a bummer.
When we look at men and women, women in general have more fat around their bum than men, but a patient does not necessarily need to be obese in order for the injections to fail. The size of the needle is only 3 centimeters or 1.25 inches, which isn't that big to begin with.
You know what's coming, don't you?
What we need is longer needles. For example, a 5 centimeter length needle as opposed to a 3 centimeter length needle.
But just how much bigger is a 5 centimeter needle?
That is
Really intimidating. It's very long.
Oh my God! No, I'd rather that one than that.
Yeah, that looks worse.
That's thicker. It's going back to the Victorian ages, isn't it?
You know, it doesn't need to go in that deep.
Yeah.
No, give me the old one, please. That's a big one.
So the moral of this pointy problem is, if you want your medicine, but you don't want to be pricked by one of Dr. Chan's extra long needles, you better get your bum into shape. In a moment, we're off to Japan to meet a scientist who's got a smaller chopper than James Bond. But before we get too excited, let's retire to the test department for a nice cup of tea and the answer to one of science's greatest questions. It's happened to us all. You're lost in a juicy mag, you reach out for your toast and knock it off the table. Sod's Law says it will always land butter side down. But will it? Enter the Toast Tester 3000 machine. The question, out of 100 pieces of toast, how many will land butter side down? And the answer? A staggering 89%. So toast does appear to land butter side down. But why? Well, here's our theory. A piece of toast falling from a table 76 centimetres high will rotate through approximately 180 degrees, which is why it lands butter side down. So, if we double the height of the table, will it land butter side up? Let's see. Amazingly, when we dropped our toast from twice the standard height, it landed butter side up 81% of the time. So, toast eaters of the world, you have two choices. Double the height of your table, or place the toast on your plate, butter side down. From solving the problems of falling toast, Experimental has headed to Japan in search of a man who thinks he can solve this, the Tokyo rush hour.
You can't go in the direction you want because you're pushed with the flow of people.
Yeah, and people bump into you. It can be painful, especially if it's a girl because you get hit by a bag.
Someone stepped on my foot with heels once, and that was very painful. I cut my foot.
Even after midnight in this popular part of Tokyo, there's still lots of people and far too many cars. Someone should do something about it.
Well, thankfully, somebody has. Here in Matsumoto, at the edge of the Japanese Alps, a new invention is taking off, and it's set to help you rise above the rat race, literally. It's called the Gen H4, and it's the brainchild of inventor Genai Yanagasawa, better known to his friends as Gen.
It's the smallest one-man helicopter in the world. It took us 15 years to develop. It's very light and very small. You fly it in a small space. Anyone can ride it, and I'd like everybody to be able to use it as casually as you'd ride a bike.
It's so light that you don't need a pilot's license to fly it, and the controls are unlike any other helicopter in the world. They're simple.
You control the height by moving this throttle, and that means you control the height with just one hand. There's one bar, and that controls direction. It's directly attached to the rotors, and if you keep it straight, you hover on the spot. When you want to move backwards, you just push the bar forwards, and if you want to go forwards, you just do the opposite. And that's all there is to controlling it.
Thanks to those pesky laws of physics, when you spin something with a motor, the motor itself tends to spin in the opposite direction. Standard helicopters solve this problem with a second vertically mounted rotor on the tail, which keeps the helicopter body still. Gen's helicopter doesn't have a tail, but it solves the problem in a different way. The two sets of blades spin in opposite direction, so the twisting force of each rotor on the body is cancelled out, giving it perfect balance.
Ever since I was very small, I always wanted to go into the sky. I think it came from reading the tales of the Arabian Nights, and the idea of flying carpets stuck in my mind.
When designing his flying carpet, Gen started with a blank piece of paper and built up the features of his chopper around 4 super light engines. Gen's engines are a miniature engineering wonder. They weigh just 3 kilos, but can produce 10 horsepower each, making them one of the highest power-to-weight ratio motors in the world. The Gen H4 is now available to buy, but it will set you back a cool 3.5 million yen. That's around £19,000. It's a lot of money, but would you be tempted?
If it was a two-seater, yeah?
Yeah, if it was a two-seater.
Or a four-seater, so the whole family could ride in it. Oh, but then it would just be an ordinary helicopter, wouldn't it? About 3 million yen? That's quite affordable. Can I really buy it for about 3 million yen? That's cheaper than a car. Yeah, wicked.
It's great. I want one. I want one too. With this, when there's an earthquake. You're right, you could escape. There's so many earthquakes in Japan.
So, a thumbs up from the Tokyo commuters. But before you get all excited, there is one tiny drawback. The Gen H4 is a bit of a fair weather freak. We've had to film it indoors today because it's a little bit windy. And that's all it takes to throw this little chopper into a tiz.
The weight is still a bit too small against the strong wind. I feel it's probably a little bit weak. For this, we're developing a helicopter with an integrated automatic control system, so it can tolerate a strong wind. And I think it will be better with this in the future. I wanted to create a one-man helicopter that anyone can ride, not only the rich people, but I want everyone to use this as you might ride a bike. My dream is that everybody flies above the cities like dragonflies. I'm working really hard for such a dream.
Still to come on Experimental, TV dinner for life, goats that just fall at your feet. But first, we're off to the test department to look where no man should look. The demonstrators are getting excited with the arrival of Hamish McQuasion, a renowned scientist with an interest in the internal pressure of bagpipes. But that's not what the test department are interested in. They want to know if it's true that Hamish has a tattooed thigh, a secret that Hamish does not seem too keen to reveal. Sometime later, when Hamish heads for the showers, our test department demonstrators decide to wreak their revenge. What our two demonstrators want to know is just how fast a Highlander would have to be flung before his kilt would rise and reveal his all. And for that, they're building a Kilt Riser 3000 machine. The theory is that if you spin a Scotsman, centripetal force will cause his kilt to rise.
Oh, that's better.
Let's see. At 10 revolutions a minute, things don't look so good. But at 15 revolutions, there is a definite stirring of the cloth. So what happens when we twiddle the kilt tester's knob all the way? So there you have it. Conclusive proof that a Scotsman will reveal all at precisely 23 revolutions per minute. Meet Charles Darwin, Mr. Survival of the Fittest. The theory being that if you can't avoid being eaten, you're history.
It's a bit more complicated than that.
It must be. Otherwise, it could not explain the continued existence of these little creatures. Tennessee fainting goats, favourite flock of farmer Gene McNutt.
Tennessee myotonic goes pretty much like any other goat, except when they get frightened, they'll fall over into somewhat of a faint, stiffen. A few seconds, they get up and act like just any other goat. They'll carry on and go on.
In fact, the goats don't actually faint. Rather, as soon as they get scared, their muscles stiffen up and they fall over. It doesn't hurt them in any way, and after a few seconds, they get up and trot away as if nothing had happened. However, those few stiff seconds is all it takes for a predator to have an easy meal. So what's causing these goats to drop at the worst possible moment? Meet fainting goat whiz kid, Dr. Al George.
The fainting goats have a condition known as myotonia, which is an inherited abnormality in muscle, which leads to a disturbance in the ability of the muscle to relax. This leads to their characteristic falling behavior in the field.
Oh dear, seems Mr. Darwin's theory is in trouble. Surely the myotonic goat is no more than lion fast food. Lion roars, goat falls down, lion eats. This is not survival of the fittest, Mr. Darwin. It's survival of the unfittest.
Shows how little you know about my theory. Now, sod off, I'm eating.
OK, so we can't disturb the great man. So let's go to the next best thing. Darwin expert Professor Abbott.
Survival of the fittest was a phrase that Darwin was initially uncomfortable with, and he eventually accepted it because of its simplicity. Imagine a population of, say, deer. And some of these deer run slowly and some run faster. And imagine there's a predator chasing these deer. It's a very simple idea that the individuals that run faster from the predator are more likely to survive and thus will fit better in their environment because of that trait of running faster. And if this happens over time, then eventually the population will evolve and become better fit. In other words, will be made up of nothing but fast-running deer.
Which cannot be why these goats are surviving. Let's face it, running away isn't an option for them. So what is their secret? Are they poisonous or something?
If you think about it, if you open up your fridge and you look inside your fridge and you open up your vegetable drawer, what you see is the product of hundreds, if not thousands of years of natural selection by breeders. With the myotonic goats, presumably the farmers that breed myotonic goats find the fainting or myotonia to be a trait that they actually desire in their goats. That's still natural selection, but the agent of selection, the hand of selection, is the farmer himself rather than a predator or a parasite.
I couldn't have put it better myself, lad.
So, far from being a proof that Darwin was wrong, the so-called fainting goat wins out over its rivals for two reasons. Partly because their condition makes for larger muscles, and therefore more meat, which farmers like, and partly because they live in a special environmental niche, where the predators are kept out by a man-made fence. Say goodbye to the fence, and we'll say goodbye to the myotonic goat. In a moment, we're going to discover where the male member is located. But first, we're off to the test department to find out just how quickly we can poison one of our favourite demonstrators. In the test department, they're throwing a party. And no party is complete without cakes. But Horace fumbles and suddenly, disaster strikes. Clearly, he's heard the old wives' tale that if you pick food up off the ground, within 5 seconds, it's safe to eat. The question is, Horace, is it true? The thought behind this pearl of wisdom is that it takes time for nasties like bacteria and viruses to stick to things. Pick it up quickly, and they won't have had a chance to hitch a ride. So, how can we test this theory on our party cakes? Well, how about using one of these, a UV black light? Pretty nifty, isn't it? Instead of using bacteria, we're going to use this fake gunk. If any of it ends up on our cakes, it will glow bright blue under the UV light. So, let's begin the test. The cake on the right is getting just 3 seconds of contact with the gunk, while the cake on the left gets a full-on 10-second plunge. More than enough for any nasty to stick to it. Now let's give them a flash with the light to see if there are any blue bits showing, and yes, both the 3 and the 10-second cake are now nicely iced with our fake bacteria. And, no doubt, with the real stuff too. So next time you drop some food on the floor, keep it well away from your chompers. Or suffer the consequences. Finally, on Experimental, we've travelled to Frankfurt in Germany, a city where the women have some rather odd theories about their menfolk.
Their brain dropped down to their pants. Sorry, but that's how I feel about them, okay?
Oh, okay, fair enough. But is there any truth in this slightly bigoted assessment of the male of the species? Let's meet a man who's interested in finding that out. Dr. Christian Kell, a neuroscientist who's determined to find out not just how much of a man's brain is in his pants, but which bit of his brain is down there. It's all part of a project to map which parts of the brain are used for interpreting the sensation of touch. To achieve it, they used a functional magnetic resonance imaging machine, a man and a toothbrush. The machine can see inside your brain as it works. The toothbrush, well, that can stimulate both your toe and other bits you might want to study. For years, we've known the somatosensory cortex, the strip of brain running up from behind the ears to the top on each side, is concerned with touch. And since the 1950s, scientists have assumed that the parts of the cortex that deal with the parts of the body are laid out like this. The head here, the hands here, the legs here, and for some strange reason, that part that should be between the legs, here, underneath the bit that deals with your feet. So what did Dr. Kell and his toothbrush find out? Was the old diagram correct?
There is a huge area devoted to the analysis of the hand, and lateral to it, another big area, which is the representation of the human face. This is due to the fact that in these regions, hand and face, you've got lots of receptors, you've got a high degree of discrimination in these areas. So there's more need of analysis, more need of computation. So the areas in which those body regions are represented are bigger than other body parts.
If our bodies were in proportion to the amount of brain dedicated to them, your average human would look like this. All head and hands.
Hi.
Nice. But what about the penis, which, according to the textbooks, should be beneath the bit of brain dealing with the feet? Let's find out how much brain that takes up.
We stimulated the tip of the penis and the shaft of the penis, as you can see here in green and in blue, and those two activations lie in the same spots. Therefore, the representation of the penis is very small.
But that's not all. According to the past experts, the area of the brain that should be lighting up is a bit beneath the area that deals with the toes. But when Dr. Kell's assistants started stimulating his subjects, they found that the bit that lit up was in fact right here, where it should be, between the bit of the brain that controls the abdomen and the bit dedicated to the legs. In so doing, they rewrote 40 years of medical knowledge.
We put the penis back where it belongs.
A massive coal plant cleans up its act and lights up millions of homes with explosive power. This mega roller coaster cranks up the biggest scare for your buck. A thrill machine that runs on gravity. A half-megaton telescope takes intergalactic snapshots from millions of light years away. And a pin-setting robot cleans up our game with surgical precision. Let's take a look inside these machines and see how they work. This is Drax, a coal-fired power plant in England. The size of 2 Manhattan Central Parks, side by side. This machine puts out almost 4,000 megawatts of power, enough to light up 5 million homes. This new-style coal burner has found a way to process and burn an old-style fuel. And it does it so efficiently, it's now among the cleanest mega coal plants in the world. Let's see how it works. Drax burns up to 36,000 tons of coal every day. That's 26 train loads. The trains dump the coal into giant hoppers. They slow down, but never stop. Every month, they dump enough coal to fill a 70,000-seat football stadium. But Drax doesn't burn chunks of rock. It's not explosive enough. So, it converts the coal to dust. A network of conveyors sends the raw coal to these pulverizing mills. Each mill has 10 one-ton steel balls packed together on a track. Coal drops into the mill through here, and the ring of balls crush the rock. A single pulverizer makes 36 tons of coal dust in an hour, and Drax has 60 of them. The coal dust is now an explosive fuel, lit up by propane and oil burners. This coal, dust, and air mixture burns at over 2,000 degrees Celsius. Each boiler is a mega kettle with flames 5 stories high. 10 stories above the flames, inside a network of steel tubes, water transforms to high-pressure steam, hot enough to melt lead. Drax is now ready to generate some serious electricity. The steam heads to the turbine hall. The turbines are housed in 6 units, each the size of a locomotive. Inside, 5 steam turbines. Each spins a drive shaft connected to a generator. When the steam hits the turbines, its explosive pressure spins the blades at 3,000 RPM. The blade tips travel at 1.5 times the speed of sound, pumping out 1,000,000 horsepower. That's the same as 6,500 passenger cars. So, burn coal, boil water, make steam, and spin 300 tons of stainless steel at Mach 1.6 to create 23,000 volts of electricity. Voltage measures how powerfully electrons flow through a wire. And Drax needs much more than 23,000 volts to get power to its millions of customers. To ramp up its voltage, which helps electricity travel great distances, you need a transformer. Drax runs the 23,000 volts through a series of copper wire coils, each wound around an iron core. That creates a magnetic field. Power jumps from one coil to another. When it goes from the looser coils to the tighter ones, the voltage increases. The transformers at Drax take the 23,000 volts from the turbines and step it up to 400,000. Which is great for the national grid. But what about this stuff? Burning coal is dirty business. It belches out harmful gases that cause smog and acid rain. Drax captures 90% of these toxic emissions before they hit the atmosphere. Smoke blows into these electrostatic precipitators. Toxic particles cling to these metal plates like fridge magnets as the smoke passes through. But that filtered smoke still contains sulfur, the culprit in acid rain. So, before it's sent to the smokestack, it's cleaned again. Every week, 10,000 tons of limestone is crushed into powder and mixed with water to form a slurry in this giant blender. When smoke is pumped through the slurry, sulfur is chemically locked into it. The resulting combo makes 750,000 tons of gypsum every year. The stuff that makes drywall and plasterboard. There's one last problem. The power plant still has huge amounts of steam to deal with. Once it's done powering the turbines, the steam needs to get back to the boilers for reheating. But first, it needs to turn back to water. So, the steam tubes are cooled by an outside source, a heat exchanger that uses river water. Drax uses 160 million liters of it every day from the river Ouse. But while cooling the steam tubes, The river water heats up to the boiling point. To protect the local ecosystem, it has to be cooled before being returned. Enter the cooling towers. Drax has 12, 2 for each boiler. The base of each one could hold the dome of St. Paul's Cathedral. The heated river water is piped into the 20-story towers, then drops through tightly woven plastic and turns to a fine spray. As heat rises, the towers draw a cool draft from the bottom and up through the falling droplets. The cooled water drops into ponds at the base of the towers and releases back to the river, cleaner than when they took it out. 36,000 tons of coal burnt up in a day, recovering most of its toxic emissions. This machine has always been powerful, but recent innovations have turned it into one of the cleanest plants of its size in the world. An over 1 kilometer track built on 20 stories of concrete and metal. The Ride of Steel is a machine designed to give you the biggest scare of your life. Doing 120 in an open-top mini-train is scary enough, but not nearly as frightening as this. For 2 whole minutes, you're locked into a bucket on wheels. The job of this machine is to keep you alive, with no engine, no steering, and no brakes. Here's how it works. You're on your way, and the initial climb slopes gradually to a height of 65 meters. 12,000 well-oiled moving parts make up the large gear and chain assembly that pull you to the top. While butterflies churn in your stomach, any one of those parts can snap without warning. But over 40 sensors monitor the climb. And if the chain breaks, magnetically controlled safety locks stop the train within seconds. The first hill on a roller coaster is always the tallest. It has to be in order to harness enough gravity to launch you 1,600 meters to the finish. 50 seconds into the ride, the train free falls into a near vertical drop. Zero to 120 in under 2 seconds. Way faster than most dragsters. As you drop, you're weightless. Any falling body weighs nothing while in free fall, until it hits something. Fortunately, you're locked in by the lap bar. Without that, you'd be airborne, flying 3 stories above the track. The force exerted on the cars as they corner around the track is more powerful than what's experienced on a space shuttle launch. So, to keep the train on the track, the undercarriage has 3 sets of wheels built in all directions to handle every dimension of flight. These are the load wheels. During the most intense maneuvers, they absorb nearly 4 times the weight of the car. That's over 50 tons of force. The guide wheels keep the car centered as it shifts from side to side. And the upstop wheels grip the car on the track during its most extreme maneuvers. 65 seconds into the ride, you're halfway through. Just when you think you're slowing down, you hit the Ride of Steel's double helix at 100 kilometers an hour. And while your brain thinks it's going in a straight line, your body is lashed to a train that is clinging to the edge of a circle. Up to 4 times the normal force of gravity pins your body down. That cell phone in your pocket now weighs as much as a kilogram. You've been flying for almost 120 seconds, and the end is rapidly approaching. Remember, this is technically a runaway train. It has no brakes. And you've got to stop in under 3 seconds. You're going off the rails. Regular brakes on this train would tear the cars apart. So the designers decided to stop the train from the outside. And they used some of the most powerful natural magnets in the world to do it. When copper fins fixed to the sides of the train slide through the magnets, they create a swirl of opposing currents. This magnetic braking stops the train in just 2.8 seconds. The designers of the Ride of Steel had a plan. Build a giant machine, insert humans, scare them half to death, and bring them back alive. And it worked. When scientists peer through a high-powered telescope, they may like the view, but they always want a better one. So, they came up with this. It's called the Large Binocular Telescope, or LBT. It probes deeper into the cosmos than any other instrument, and it has 10 times the resolution of the Hubble Space Telescope. A telescope is basically a magnifying glass. It focuses light that enters here onto a single point. In this case, a mirror located here. This bounces the light to an eyepiece that magnifies it even more, up to 60 times. That's pretty good, but its vision is still limited. Big glass lenses are hard to make and distort light, which is why the best telescopes use mirrors. Set 3,000 meters up this Arizona peak, the machine took 2 decades to build. It's a new generation telescope that reaches the edge of the universe, hoping to shed light on some of its unsolved mysteries. That's a tall order, but it's a big machine. The LBT is 2 telescopes in one, with its giant pair of binoculars and 2 of the world's largest mirrors, 16 tons apiece, spanning 8.5 meters. Working together, they capture more light than any telescope ever built. Starlight bounces off the 2 primary mirrors onto 2 smaller secondary mirrors, and then back down through this center hole to where researchers can see it or record it. But all this size doesn't do much for resolution. So LBT has to overcome the 3 optical challenges of any Earth-bound telescope: keeping up with the rotation of the Earth, fighting gravity that distorts the shape of thin mirrors this wide, and keeping focus through the density of the Earth's atmosphere. First challenge, get a fix on a target and compensate for the Earth's rotation. This half-megaton machine has to position itself within a millionth of a centimeter. That's about the thickness of a strand of DNA. May sound crazy, but it's done with this altitude azimuth mount. One axis turns with the Earth, the other tweaks the elevation. A point-and-control system translates the location of the object in the sky into geographical coordinates and locks into them as the Earth moves. The entire telescope incrementally shifts on 2 giant C-shaped mounts, like a big rocking chair, floating on a super slick film of oil. It's so perfectly balanced that all it takes is a set of 4 puny lawnmower-sized motors, one on each axis, to spin the heavy LBT a full 360 in just 4 minutes. The outer building rotates in sync with the telescope as it rides on its own rail system. And it does it to within 1.5 degrees of accuracy, even in gale force winds. The second optical challenge it needs to solve is gravitational distortion of the primary mirrors. The mirrors are so large, so thin, gravity actually warps their perfect parabolic shape. To correct this, there are 160 computer-controlled actuators underneath each primary mirror. These are like pistons that push up on the mirror to correct its parabolic shape and restore the image. The third optical challenge for the LBT is correcting distortions caused by the atmosphere. Stars don't really twinkle. It's the effect we see through atmospheric turbulence or haze. To lock that star's image into a single steady point of light, LBT locks onto a reference point, like a bright star that's already known. Computers measure the real-time angular distortions in the star's image to determine how much and what optical adjustments are needed to correct those distortions. 672 magnetic coils line the back of the hair-thin secondary mirrors. Each coil moves the surface up and down 1,000 times a second. The adaptive mirror surface actually distorts in real time to mathematically compensate for the angular distortions on the reference image. With the three major optical challenges figured out, the LBT has one more trick to help it see better than ever before. It ramps up its image brightness by swinging this pair of third mirrors into place, combining its binocular images into one super bright picture. That results in images like this nebula, over 113 million billion kilometers away. The LBT is the most powerful single-mount telescope in the world. A heavy, rock-solid machine tamed by precision feather-touch controls. Its sole purpose is to capture and translate light into pictures of places we can only dream of visiting. "95 million people all over the world throw a ball like this one and knock down billions of pins year after year after year." Not that long ago, teenagers used to reset these pins by hand, but that left restless bowlers waiting for the next shot. This robot is about to turn 50, and it never stops working. No lunch break here. It's cheap to run, doesn't suck up a lot of power, and it's fast. The Brunswick A2 pin setter can sweep up and rack a set of pins in just 9.2 seconds without fancy software. Just 4,000 moving parts that run like a clock. Let's see how it works. A typical throw will launch the 3 to 7 kilogram ball into pins made from hard rock maple at over 30 kilometers per hour. The pin setter waits for its cue. When the ball passes this electronic eye, two things happen. A relay switch tells the A2 to get busy, while a camera snaps a picture and sends the data to the scoreboard. The A2 locates the standing pins and snatches them up, while a sweeper clears the pin deck of fallen ones. The same pins are then set back down in the exact position the bowler left them in. Back in the pit area, the fallen pins separate from the ball. A belt sends the pins to the top of the machine, where they drop into a metal tray called a turnaround pan. The weight of the pin's body makes it drop heavy part first into the pan, so they always load right side up into the distributor wheel. Each time a pin loads, it triggers a clutch, which moves the carousel into the next position, ready to take the next pin. While all that's going on, the A2 gets the ball back to the bowler ASAP. The ball makes its way through here to an elevator. And from there, it rolls along a downslope tunnel as gravity sends it back to the player. At the end of the shaft, a series of motorized rollers send the ball up this S-shaped curve. It all happens in about the same time that it takes to tie your shoes. After the bowler takes his second and final shot of the frame, the sweeper clears any remaining pins. Sensors on the pin deck detect that there's no more standing wood. So, it sends a message to the distributor wheel to release the pins, all 10 of which are reset. The A2 automated pin setter machine completes its cycle like it has every day, every year, and every decade. Smoothly and efficiently. This old boy rarely keeps a bowler waiting.